Hi, we've got a brand spanking new Rigol. It's the HDO4000 series, and the nerds on the EEVblog forum are absolutely going to burst unless I open this thing up and do an unboxing and first impressions measurement type thing, because this uses the new Rigol Centaur chipset in this thing. The previous Phoenix chipset was the previous one, isn't it? It's the new Centaur chipset, and it's a full 12-bit hardware scope with an ultra low noise front end, supposedly. So that's what everyone wants me to initially check out. So let's do an unboxing here. This is the HDO4000. They've actually got also a HDO1000 series, which will be coming in another 2 weeks. So if you want a lower cost one, check it out. This one starts from $26.99 US, but that's for 4 channels, 200 megahertz, 12-bit, you know, touch screen, touchy-feely, all the rest of it. So let's have a squiz. What else we got in the box? Nothing. So there we go. And it's black. And yeah, it's gonna, I want to count the number of fonts on it, because of course Rigol are famous for not exactly having the greatest industrial designers in terms of like look and feel. Anyway, any color you like, as long as it's black. There it is. This is the 200 megahertz model. Yeah, so this is the $26.99 US model. I don't know if it's software or hardware bandwidth upgradable, but for $36.99 there's the 400 megahertz version, and for $46.99 is the oddball, quite oddball, 800 megahertz version. Anyway, 4 gig samples per second, 12-bit, and that's none of that boxcar averaging rubbish. That is apparently a true 12-bit converter in this thing. Whether or not it runs at the full 4 gig samples per second, I don't know. Anyway, there is a new HDO1000 series also, which, as I said, I'll get in a couple of weeks, and it starts from like $699, and everyone's pretty excited about that one. Anyway, this is all touchy-feely apparently. Soft button, power, I don't know what wankery's going on here. Yes, it does have the active probe interface, very nice, Rigol specific, of course. Each manufacturer has their own standards for that, but of course, you know, in this sort of price bracket scope, you'd expect that. So yeah, it does have 50 ohm input and 1 meg 19 puff, is it? And we've got dual USBs on there. And what do we get on the back of this thing? I do believe it comes standard with 10 meg reference output. That's nice. 10 meg reference in, external trigger and auxiliary as well. Kensington lock, HDMI output as standard, fantastic, USB device, and LXI LAN as well. The HDMI output is handy, of course, because you can, you know, feed it into projectors and capture systems and all sorts of stuff. Really good. Bloody, yeah, weird ass mains plug, and looks like we're going to get 350 meg probes. So there you go. Ooh, it's got a little spinny back on it. They feel rather cheap. I don't know. And they are a switchable 1-to-1, 10-to-1. Yeah, 350 megahertz and 35 meg, which is actually quite high for the ×1 position as well. But that's good, because you want a higher bandwidth, because this supposedly has a really low noise, ultra low noise front end and a 12-bit converter. So, you know, one of the things key things you'd be buying this bad boy for is for like low signal measurement capability. There you go. It would have been calibrated just before it was sent to me, like the day before or something. So anyway, you do get a cow sheet and a USB cable, and that's all she wrote. Well, I just plugged it in, and it's got a permanent standby LED there. The fan whirred up, and I saw the Ethernet lights flash and everything. Anyway, let's see how long it takes to boot. Oh, geez, taking its time. Anyway, it is a 10.1 inch 1024 by 800 HD display. Supposed to have 1.5 million waveform updates per second. I don't know if I'll test that in this video, but up to 500 meg points of memory apparently. Well, we're in. Okay, so that was about 35 seconds or thereabouts. So yeah, the screen is really high resolution. I like it. It's not too glary. You know, we're going to get some reflection, but no, it's not super glary at all, so that is a bonus. So whether or not you actually like the interface or not is, well, you know, it's anyway, they haven't got the separate channels for each vertical, separate controls for each vertical. Of course, you can't do that on a scope this big, but Yeah, I'm not a fan of the black. I'm not a fan of the look and feel, but who cares, right? You're buying this for the performance and supposedly the ultra low noise. And watch this. 10, 5, 2, 1, 500, 200, 100 microvolts per division. It's already set 20 meg bandwidth. So yeah, because of the 12-bit converter, it actually can offer 100 microvolt range. So we'll see over what bandwidth that's going to do it. Of course, you won't get, I guarantee you won't get the full 12 bits at 100 microvolts. I really like that. That interface looks really jazzy. Look at that. They show the, the proper system path. It does have input grounding. There you go. So the coupling, we can actually ground that sucker. 50 ohm termination, 1 meg, and they call it bias, but that's basically vertical position. And then we've got bandwidth filter here. What do we got? Oh, 20 meg on, off and on. Is that it? They don't have 100 meg or something like that. No, it's skew and stuff, and then a trigger. Anyway, I rather like that. They're giving it like a systematic view there. And then you can go over to channel 2, even though that's not enabled at the moment, and you can turn it off and on. Of course, you don't have to use that interface. You could just use the controls. Is it got a touch? Is there a touch button off? Touch lock? That'd be it. Yeah, touch disabled. So if you don't like the touchy-feely and you're a screen poker like I am, yeah, touchscreen can be annoying sometimes, other times very valuable. Anyway, apparently these rotary encoders, they do have detents on them. Apparently these are optical. These are not electrical wipe contacts. So that's one of their banner advertising specs. You might see that in the teardown. But yeah, they claim longer life. Now, one thing I'm really not seeing here is, and that's supposed to light up blue. Yeah, it is. Maybe so I've got studio lights directly. I turn those off, and then I'll turn my overhead lights off here. And yeah, once it gets real dark here in the lab, I can kind of, sort of see that that's blue and lit up. But, oh, geez, it's, oh, gee, I can barely see that. Not a fan of that, but, little things. But you'll notice one thing, this is lacking, of course, this is not a mixed signal scope. They're obviously not interested in the mixed signal market. What they are interested in is like the ultra low noise, 12-bit. That's why you're buying this scope. You're not buying it for mixed signal capabilities. So there appears to be absolutely no option for it, although, of course, with 4 channels, you could do some, serial bus decoding and stuff like that. Not sure if it's included or not. Once again, this is just an unboxing. So what does this little Rigol menu down, big Rigol logo, look, this is very Rigol looking. Look at that. Look at that. Doesn't do anything. It's just a big R. Anyway, I do like the layout here. Of course, we're getting the full width of this 10-inch screen, so it looks very nice. Oh yeah, that's the auto setup button. There we go. There's our, oh, look at that. Oh, look, you can see the detail. You can see the detail on that bad boy, and automatically it's popped up with this, okay, to give us a different time base option right off the bat, and then it vanishes. Neat. Anyway, right off the bat, it's showed up with our statistics here for our period and our frequency. There you go. So at this particular time base, that's how many samples, it's waveform updates per second we're actually getting there. All right, so we just go horizontal like this, fairly responsive, position up, down, yeah, like in that, press for, oh, press to center. Hello. And please forgive the overexposure of my hand and stuff. Like this whole thing is black. It makes exposure on camera very difficult. Where the hell's my waveform? Oh, looks like I accidentally hit channel 1 there. Anyway. Oh, okay, the ground's not in the center. That's why it's not going, but it does have push to go center. So, yep. No worries. Pop up the keyboard there. There you go. That just allows you to rename the channel there, English and Chinese, right off the bat. So what capture options do we get here? Acquisition, normal, average, peak, high res, and ultra acquire. I think the ultra acquire is the 101.5 million waveform updates per second, so that would, I'm sure, severely limit the memory and stuff like that. Anyway, memory depth 10K. What have I got standard? Hello. Oh, there it is. 250 meg. Okay, and what happens if we go ground, internal ground? Oh, like, yeah, the internal ground, that is not a real measurement. It's just software grounded, that, so that's just meh. Okay, but you might turn that on. Probably, maybe it does actually physically have a relay and short in there. We'll have to have the teardown, but certainly there is no way that, I mean, I'm at 100 microvolts per division, okay? There is no way that is sampling, right? That is not real. Just disabled it. Yes, it might be ground in the input, but we can't actually do a measurement on that. It just means maybe reducing crosstalk for the other channels or something like that, perhaps, would be the only advantage to that. Anyway, so I'm going to leave that at DC coupled. 1 millisecond per division, 250 meg points. Now we want to measure this. So let's measure, okay? So volts peak to peak, volts RMS, and AC RMS as well. I've done a whole video on AC RMS. Anyway, it does have a lot of measurement. Oh, pre-shoot, look at that, overshoot, and stuff like that. So, they've got lots of options there for measurements. I like that. Anyway, what we want to look at is noise floor. It claims 18 microvolts, at least one spec I found, 18 microvolts RMS, ultra low noise. I'm getting 25. So once again, this will depend on memory depth, time base, all that sort of stuff, okay? So can we actually expand those and get stats on any one? Yeah, look at that. I really like that interface. It just, like, you don't have to enable. It looks like you don't have to enable stats. You just drop it down and you can put it up. Like, you know, if we didn't care about the frequency and the period anymore, we can just, bugger those off. If we click on that, indicator setting, reset statistics, remove, all that sort of jazz. Yeah, anyway, I'm liking the interface. This is good. Now, for some reason, the count has reached 1,000 and it stopped. Reset stat. There we go. What, it stops at 1,000? That's a bit disappointing. Okay, I'll just leave it running and see if it actually... Oh, it reset them all. It reset this one as well. And there's nothing wrong with that, of course. It's just the way it works. AC RMS is around 25 microvolts. Not quite down to the 18 microvolt spec, but getting there. Okay, we're coming up on 1,000. Yep, it just stopped at 1,000. That's disappointing. Why? So anyway, when I move that, acquisition totally stops, and it's chopped off half my waveform, but there you go. Okay, it's a bit... Whoa, way. I don't know. It's very, it's just very touchy down to the 100 microvolt range. So what I've done now is actually set the other three inputs to internal grounding. So like I've shut them off and it doesn't seem to be any different. The RMS here, if you just do your regular RMS measurement, I've done a video on this, as I said, that includes the DC offset there. So your AC RMS is effectively mathematically removing that AC. So this is one you want to use. AC RMS, also called standard deviation as well on some scope. Now, does this change with the bandwidth limit? Let's have a look. How do I turn the bandwidth limit off? Maybe I can't at this, where once I went to 2 millivolts, I thought that might be the case. Yep. Come on. Bloody touchscreen. It's like there's a delay there. I've noticed this like a few times and it's kind of like annoying. Maybe I've got to get used to it and learn how to drive it. But yeah, I thought it might do this. When we're at 1 millivolt per division, we get the ability to turn the bandwidth limit off like that, and we can actually repeat the noise measurement like this. Okay, so we can reset that. You can see now physically it's going to be higher. We're now up to 105 microvolts RMS now. Yeah, it doesn't matter. Anything under 1 millivolts has its own, is exactly the same noise floor on those ranges on the 100, 200 and 500 microvolts. Alright, I found an annoying bug that already made me come a gutsa once and give me incorrect noise measurement results. You'll notice I've got 20 megahertz bandwidth limit turned on. I'm 2 millivolts per division. Let's go down to 1 millivolt per division. Okay, so it's on, and I'll go down to 500 microvolts per division where it forces the 20 megahertz bandwidth. Okay, and watch what happens when I go back to 1 millivolt. It vanishes. It disables it. And you'll be able to see this on the noise level here, okay? With the bandwidth limit enabled. Okay, I go down to 500 microvolts, and then I'll go back up to 1 millivolt, and you'll notice that the noise has jumped up because we're a higher bandwidth. That's what you expect. But yeah, they need to fix that. So this is how I'm going to standardize my noise measurements. 1 millisecond time base, 1 meg point memory here, and then we're going to get the AC RMS figure. That's the only one we care about here. And I'm currently at 1 millivolt per division. So reset the statistics, and this is full bandwidth on the 1 millivolts. We're talking 55 microvolts RMS noise, AC RMS noise. And if I turn bandwidth limit on, notice it's much smaller there, 20 megahertz bandwidth limit, 17.3 microvolts. So it certainly meets its 18 microvolt spec on 1 millivolt. And if you read the fine print in the manual, it says the 100 microvolt, the 200 microvolt, and the 500 microvolt ranges are just software expansions of the 1 millivolt range. So it doesn't have a true 500 microvolt range. That's why the noise figure, if I change it down to 500 microvolts, it's exactly the same noise. And this is with a 50 ohm terminated input. And of course, if I take off the 50 ohm terminated input, then yeah, that's what you get. Jumps up to about, once again, 500 microvolts, 42 microvolts, thereabouts. And as far as the bandwidth goes, we're getting about 240 megahertz. So that's, you know, slightly above the ticket value here with 1 volt RMS signal. And the 1 millivolt bandwidth for a 3 millivolt RMS signal, there you go, 3 dB down at the same 240 megahertz. So yeah, we've got the same bandwidth there. But as I said, if you switch to the 500 microvolt range, even though it's only a software expansion of the 1 millivolt range, it puts on the 20 megahertz bandwidth. So don't know what's doing there. See if you can see this. Like, I move it like this, okay, and there were jumps. Like, I'm not sure, maybe I can't reproduce it. Well, see, it jumped back down. What the? So we'll go up to here, and let's turn on some averaging, shall we? Yeah, it has some new flex knob thing here. So, yep, there we go, 64 averages, there you go. That'll do the bit. Whoa, no, because we're not triggering properly. There's your problem. There we go. So that's our 100 microvolt signal averaged out, because, like, you know, I don't know the system end-to-end noise of this. I can't remember the spec of this, so I'm not going to look it up, right? But anyway, we can definitely see a 100 microvolt signal on there. It is actually only 71 microvolts, so I don't know what's doing there. Maybe we're down at the limits of the accuracy of the SIGGEN or something. I don't know. Look, this is not a detailed, comprehensive thing. It's just the first impressions. By the way, it seems to be running Android here. There you go. We've got the Android version for those playing along at home. Other open source acknowledgement, document browser, thing happening. Anyway, I do like how you can just call up this and, you know, you're straight into your networking and your DNS and stuff. Aha, it looks like it is software upgradable. There it is, 200, 400 megahertz bandwidth upgrade option. I don't know, embedded serial bus trigger and analysis forever. Once again, I don't know if this is standard sort of stuff. Auto serial bus trigger, it's limited. RS-232 UART forever. Aerospace bus trigger analysis, FlexRay, audio serial bus, so I2S sort of stuff, and power analysis as well. This would be a nice tool for power analysis. Yeah. Now, I just found something here. I've stopped and captured a waveform, and if we actually zoom in on this, right, because we've got our 12-bit converter, we can go in, but watch this, right? 50 millivolts per division. It actually lets us go down to 20 and 10, and then it lets us go below 10. It's down to 1 millivolt per division, but you can see it's not actually changing on the screen. So you shouldn't actually let somebody go down to that, because then it can give them think they're actually on 100 microvolts per division, and they're not. So that is like a complete oversight. They should actually limit that. And another quirk that goes along with that, I've set up some Y cursors here, and just a note between this point and this point here, we're at 20 millivolts per division. Now, it'll actually let us go down to 10, but you'll notice it didn't double in size. It actually, and this is physically the limit if I'm down to 1, right? So it allows us to actually go down to 10 millivolts per division, where it's no longer relevant. You know, it's inaccurate there. So it should have stopped at 20 millivolts, but it didn't. It let us go down one more, which then becomes inaccurate, and then it goes down completely below that. So yeah, they need to software limit that. You know, if you're zooming in to measure stuff, you've got to be aware of this. Okay, to show you the 12-bit resolution, what I've got here, a 1 megahertz sine wave, okay, at 5 volts peak to peak, and we can zoom in, go to 2 nanoseconds per division, and we can successfully go down to 20 millivolts per division down here. Now, I've done captured the exact same signal on the Roden Schwartz here, which is a 10-bit converter, and so I've done exactly the same thing, and I've zoomed in to 20 millivolts per division, 2 nanoseconds per division up here, so it's exactly the same, and you can actually see the quantization of the bits there. There's clearly the difference in there, but you can still make it out, right? So this 10-bit scope, incredibly useful, but we are seeing more detail over here on the 12-bit, but it looks like this is doing sine x on x interpolation. I mean, look how smooth this is. So it's doing sine x on x on the displayed data. There's no way it's that smooth just for 12 bits. So I want to try and turn on dot mode and see what we can get. Just as an aside, like the Roden Schwartz that I showed in my ACRMS video, they actually show you the actual formula used for the ACRMS and the other functions. Neat. Well, either it's not here or I feel like a complete dummy because I cannot find any way to turn off sine x on x in this thing. I feel like I'm going nuts. Okay, I'm in ultra acquire mode here, and well, I'm gonna have to RTFM on the ultra acquire mode because all I do is step up the time base, and it's obviously like a segmented mode thing. Display mode, adjacent, overlay, waterfall, perspective. Wow. Okay. This is impressive. Anyway, Ultra mode is the only one where you get the 1.5 million waveform updates per second. So don't buy this scope thinking it's a 1.5 million waveform updates per second. It's only in specific frame-in Ultra acquire mode. Normal operation, no, it's apparently only 50,000 waveforms updates per second maximum. But that's, you know, still all right. And just checking the dynamic range, does it go off screen here? So we've got a waveform there. We'll stop that, and then we'll just vernier that, and we'll take it back, and there's a little bit of extra range, but then it clips. So yeah, that's not much at all. So yeah, there's really nothing doing there. So if I turn it right down to 1 millivolt, I run stop that, and yep. No, that's, there's no extra, no more dynamic range to give there. Okay, so I'm just going to test at what volts per division the noise actually increases here. So we've got 17 microvolts now. Let's call that 20. At 5 millivolts, it's 29. At 10 millivolts, it's 60. 20 millivolts, 105. 50 millivolts, 240, and 100 millivolts, 520 microvolts ACRMS. We'll leave it at that. We'll just try our 100% modulation test there for our waveform intensity for the, you know, intensity graded display. I don't think is it as good? It's not, you know, nice and bright there, and it's, I don't think it's quite as good as previous Rigols, is it? Have they changed something? Don't know. I mean, it's, you know, still pretty decent intensity graded display, but I don't know. And can we zoom out after capture? Stop. I've done a whole video on this, and yep, we can. That's handy. Okay, let's see how useful the 12-bit converter is. So I've just got a digitally generated sine wave, as we'll see in a second. So I'm going to stop that, and we're going to actually zoom into this, okay? We can actually see the individual quantization steps of the digital to analog converter. I'm generating this waveform from a Keysight 3000 series scope, so I can't remember how many bit, I think it's, is it only an 8-bit waveform generator? Anyway, you can see the individual bits, but inside there, you can actually see the noise inside. You can see quite significant noise detail inside each individual bit. And that's very nice. Let's compare that on a 10-bit scope. Okay, so we use the Roden Schwartz RTB2000, which is a 10-bit hardware converter. So we'll stop that, and we'll zoom into the same detail there. So that's exactly the same time base and scale as the Rigol, but there is the Rigol one. So significantly more detail, but I can't turn off that sine X on X interpolation that we're actually getting there. So we're getting essentially more detail in there than what's really there. And on an 8-bit scope, the Keysight 3000 series will stop that, okay, to the same 1 millivolt. And there you go. You can't see much noise in there. You can see that there's some, but you can't get the sort of detail that you can on a 10-bit scope and then a 12-bit scope there. So once again, bloody sine on X. I wish I could turn that off. I can't. So now I've repeated this exact same test with the 20 megahertz bandwidth limit on. We had no bandwidth limit before on all three scopes. I want you to note the size of the steps here and the noise relative to that. We'll go over to our 10-bit converter over here. Once again, 20 megahertz bandwidth. Of course, the quantization level is the same. We're at the same 1 millivolt per division, but you'll notice that the noise is significantly more, and you can see the quantization levels, like the actual 10-bit quantization inside that noise measurement there. So that's interesting. And on the Keysight 3000, which is an 8-bit scope, 1 millivolt per division, you can see that the noise is probably, you could even say it's slightly less than the Rohde & Schwarz RTB 2000. Now, I know the Rohde & Schwarz 3000, I think, is lower noise than the 2000. But you can see how it's significantly higher noise amplitude level in there compared to the Rigol. I mean, you can just look, check it out, right? It's much cleaner. And that's exact same bandwidth, exact same 50 ohm terminated signal and everything else. But that 12-bit converter and the lower noise floor, it's doing a good job there. Oh, and by the way, the fan on this thing is kind of like a little bit annoyingly loud and whiny. If it's just your only instrument here on the bench and you got it on, you can really notice it. So replacing the fan in that with a quieter one. Anyway, I think that's it for just the initial unboxing and first impression of this thing. And it's obviously competing against the Siglent SDS2000 HD series, which is also a 12-bit scope. But the Rigol is significantly less priced. It starts at $26.99 for 200 megahertz 4 channels, whereas the Siglent, the 2104 HD, starts at $32.80 US dollars for 4 channels, but only 100 megahertz. If you want that 12-bit 4-channel low noise system, then the Rigol is coming at a cheaper price point. But as I said, doesn't have optional logic analyzer, doesn't have a waveform gen, whereas the Siglent actually has both of those as optional. And I think, some nerds on the forum are arguing about whether or not, the Siglent is slightly lower noise than the Rigol, etc., etc. But the Rigol does have a better upper limit. The Siglent only goes up to 350 megahertz model. This one goes 400 megahertz or even 800. So the teardown will be interesting. They do have a new ASIC front end, apparently. I believe that's the same ASIC front end on the 1000, the cheaper 1000 series, which is going to start at $699. So that's kind of exciting. But unfortunately, I think they're going to software cripple it and not have less than 1 millivolt modes. So anyway, and also the Siglent has a 1024 by 600 screen, and the Rigol here is 800. So you're getting a better vertical resolution screen for less money. Now, Rigol only claim greater than 8 bits effective number of bits on this thing. They don't claim any better than that. So, the specifications, they're like really detailed, heavy specs for this thing. They're not exactly like screaming them like all your big manufacturers will go into much more detailed specs and stuff like that. But Rigol obviously are competing against the new Siglent 12-bit jobby, and they're trying to undercut them on price and bandwidth while leaving out a few optional features. So yeah, I really want to know why the 20 megahertz bandwidth limit automatically cuts in on less than 1 millivolt. It's obviously the same range. It's physically the same range. Why it software limits it to that, I don't know. They might be doing some software, ERES enhancement or something like that at the less than 1 millivolt, the 100 microvolt to 500 microvolt ranges there. So they could be doing a bit of software trickery there. But yeah, more tests required. But I wish they could turn X on X off. I can't find it, and Rigol haven't gotten back to me yet, so I don't know. Anyway, the market is really hot hotting up Siglet and Rigol and like battling it out in these 12-bit scopes. Obviously, there's other brand 12-bit scopes on the market, but you know, they're like the two competing sort of players at the same level. So it's going to be interesting to see, and I'm interested to see what the 1000 series brings as well. Brings the technology of the new Centaur chipset and also the presumably the ASIC front end as well. And just a quick test of the tap test on the input. Yeah, look at that, microphonics. Almost every scope does it. Anyway, hope you enjoyed that. If you did, please give it a big thumbs up. As always, discuss down below, and the EEVblog forum, all the nerds, all the test equipment nerds are over there talking about this stuff. So join on in. Catch you next time.